Hi, my name is Tara, and I'm excited to present my research work with Dr. Rikiya Yamashita, a concatenated convolutional neural network and transformer-encoder to diagnose cancerous thyroid nodules in ultrasound cineclip images. Incidental thyroid nodule detection has increased notably in recent years. Biopsy of suspicious nodules is the gold standard for diagnosis, but this is an expensive and invasive procedure. Currently, risk stratification of nodule ultrasounds is done manually by radiologists through the ACR Thyroid system, but this is highly inefficient and tedious and has problems of under and overdiagnosis. Our goal was to address the urgent need for computerized solutions to automate diagnosis by utilizing deep learning techniques in order to achieve superior predictive performance to ACR Thyroids. Specifically, we aim to increase sensitivity, or reduce false negatives to ensure cancer patients receive the treatment they need, and to increase specificity, or reduce false positives to avoid sending benign nodule patients into biopsy and expensive treatment. So how could we address this with state-of-the-art techniques? Convolutional neural networks can fully computerize feature extraction to improve efficiency. Our dataset contains prospectively collected and fully labeled biopsy data as ground truths, enabling effective supervised machine learning. However, the limitations of the small size of our dataset with less than 200 nodules meant our deep learning algorithm had to be quick to converge and sophisticated. In addition, we addressed two main technical challenges. First, extreme class imbalance of the dataset with over 90% benign nodules made it extremely difficult to train an unbiased deep learning model. Furthermore, it was important to process sequentiality of the video cineclips in order to make an effective prediction about the entire patient's malignancy. Standard CNNs are powerful at extracting features from individual frames to detect malignancy, but don't take patient frame sequentiality information into account. To overcome these challenges, we incorporated multiple techniques and developed a novel multi-stage deep learning neural network, the weighted CNN and Transformer-Encoder model. Overall, for this novel architecture, we employed a weighted MobileNet v2 CNN for frame-wise feature extraction, and fed features into a Transformer-Encoder model for patient-wide cineclip processing with self-attention. In the next few slides, I will break down the features of the deep learning algorithm. In order to process sequential data, we first modified the individual CNN inputs by stacking 3 frames from one patient into a single 3-channel instance. This incorporated a broader array of patient-wide feature information into one CNN input instance. We preprocessed data with 2 variants for stacking frames, equally spaced frames and adjacent frames. The second approach for sequential processing was concatenating this transformer-encoder, which I will describe later. Next, we solved our dataset's problem of extreme class imbalance with multiple weighting techniques on the CNN, taking a twofold approach. First, we implemented weighted oversampling of CNN inputs based on the benign to malignant nodule ratio in the dataset of 179 to 17. This was to increase the amount of malignant cases in model training. Our second strategy was backpropagating focal loss so that the model relied more heavily on the error produced by malignant cases than the benign cases during training. After the CNN, a transformer-encoder was concatenated for sequential processing as shown in this image. Transformer architectures have shown promise in natural language processing, but they are novel in biomedical image classification to exploit the sequential structure of cineclip frames. We utilized a transformer over an RNN or LSTM model as the transformer has a more powerful self-attention mechanism, which highlights important frames within the nodule cineclip like a radiologist would do for overall nodule diagnosis. For our application, we isolated the transformer's encoder, which includes the self-attention. We extracted features from the CNN by instance, then grouped the feature vectors by patient and fed them into the bi-layer transformer-encoder model. The Transformer-Encoder processed nodule-wide feature context to inform individual prediction probabilities, and we then averaged the individual probabilities for final patient-wide classification. We measured model performance by an area under the receiver operating characteristic metric, or AUROC, which relates classifier sensitivity to specificity, and we averaged AUROC across 5 cross-validation folds. We found that our best performing algorithm with adjacent frames had an average AUROC of 0.867 and performed superior to manual TIRADs, which had an average of 0.798 AUROC. These graphs show our models in blue compared to TIRAD's performance in red. For each ROC curve graph, the top left quadrant demonstrates high specificity and high sensitivity. And as you can see in the bottom 2 graphs, our models in blue show superior performance compared to the TIRADs in red. Both of our deep learning models performed with 12% greater sensitivity than TIRADs given the same or greater specificity. As a whole, our novel deep learning architecture demonstrated superior performance in both sensitivity and specificity compared to current manual radiologist risk stratification with TIRADs. Our dataset was small and skewed, which was a challenge, but we hope to further enhance model capabilities by training and testing on external datasets and with semi-supervised learning. Because our models are automated and fast on our real-world dataset, there are numerous applications to improve patient outcomes, including real-time complementary diagnosis along with radiologists to minimize error rate, or as a pre-screening or post-screening tool along with radiologist diagnosis for increased efficiency and accuracy. Finally, I would like to thank the team at the QIAI lab at Stanford for their work and contributions to this research.